We have a new topic for discussion today, and that is image enhancement. Now, many a times it so happens that the images that we get from the output of various sensors, okay, or the photographs which we get, okay, from some natural scenes or from indoor scenes, etc., okay, there we find that the quality of images, okay, are not up to the mark. Means quality in the sense that many a times we find that the image is having a very poor contrast. Means we can't clearly separate out the bright regions from the dark backgrounds, okay, or vice versa, okay. Or it may be that the image is very severely degraded with noise. I mean, apart from the information content in the picture, there are all unwanted details which are present in the image, okay. So that means to say that the image is affected by noise, and we may not be able to do any further processing with that image till the time that noise is removed. Or the problem may be such that the outline or the boundary of various objects which are present in the image, they are not clearly visible, okay. Means it may be due to the poor imaging condition itself that the outline of the objects get blurred with respect to the background, and we can't extract the details of the object boundaries. It may be that the image is having insufficient details, okay, or it may be that the image is having lot of extra details, many of which are unwanted, and we may like to eliminate or reduce, at least reduce some of the unwanted features from the image by applying some kind of a filtration technique on the image. So all these problems are usually there in the images, especially the images which we get directly from the output of different imaging sensors. So there is a need, okay, to improve some particular features of the image so that further processing can be carried out. Because the difficulty is that if the image quality or if the image features with which we are specifically interested, okay, they cannot be extracted properly from the image, then further processing or any kind of analysis or interpretation with those images become very difficult, okay, unless we do some improvement on those specific features. All right. So the image, the subject of image enhancement basically encompasses a number of areas, okay, some of which I am listing over here. First is improving the contrast of the image, okay, that is to say the difference between the dark and the bright regions. So the first requirement may be to carry out a contrast stretching or contrast enhancement. The second requirement could be that we would like to sharpen the edges, okay, which are present in the image. So that is to say doing a kind of edge sharpening. Or rather, many times we are not interested in the uniform intensity regions present in the image. We are only interested in the regions where the image intensities are making some specific changes, or rather extracting the edges, okay. That also comes under the subject of broad topic of image enhancement. Or the third requirement could be, as I told in the beginning itself, noise reduction. Again, just like the case of any one-dimensional signals, one-dimensional time-varying signals which you must have studied already, okay, we cannot completely eliminate noise, okay, but by applying some filtering technique or whatever, okay, we can only reduce the amount of noise which is present in the picture, which is present in the signal. Very similarly, for a picture, which is after all a two-dimensional signal, we may not be able to eliminate the noise completely, okay, but we may be able to reduce the noise, okay. Of course, how we remove the noise is again something, okay, which is dependent upon what nature of noise is present in the image. But we will study that what kind of noise reduction is possible, okay, within the images, okay. So, and then as I was telling you, okay, image filtering also comes under image enhancement. Filtering means where we would like to filter out some of the unwanted features or unwanted details in the image, okay, so that the portions, okay, which are wanted, okay, they appear in a better way in the image, okay. So this filtering is also done, and again when we do the filtering, okay, we will consider the kind of filters which can be applied directly on the grayscale values of the image, that is to say filtering in the spatial domain, and we will also consider filtering in the frequency domain, because already the transformation techniques, the different transformation techniques are well known to us, okay. So that by applying our knowledge on the various image transform techniques, we may like to do filtering in the transform domain, or rather in the frequency domain also, okay. So these are some of the areas where we will look for the image enhancement techniques. All right. Now one point, okay, should be told to you, okay, so that there is absolutely no misconception about this subject of image enhancement. I think a lot of times people have a tendency to feel that image enhancement means an overall image improvement, okay. I think we must not, at the very first place I am telling you that we must not have that kind of an idea that it is image improvement, okay, because you see one thing that in an image it is only some of the features which are not prominent to us, and we would like to improve those specific features, okay, because it will help in the analysis, or maybe that when we are presenting the image on any graphic display, okay, the quality of the image should appear better to our eyes, okay. And after all, why do we need a better quality picture as far as our eye is concerned? Again, our objective is to extract some wanted features out of the image. But one thing is there, if you think that there is going to be an image improvement, let me tell you one fact, that after all, the input to your system, okay, is an image which is degraded due to certain things, like say a poor contrast image you take, okay. Basically in that image the information itself is, the input information itself is little bit of insufficient in the sense that the input information is such that it is unable to give us a clear distinction between the dark and the bright regions, okay. Now what we can do is we may stretch the gray level values, so okay, we can make the bright regions brighter, we can make the dark regions darker, okay. All these techniques we can do, but always keep in mind that you are not adding any extra information to the image, all right. Unless you are adding extra information to the image, okay, there is no way whereby you are improving the overall quality of the image, okay. Like if it is a case of contrast enhancement, all that we are going to do is that all the bright regions we are going to make brighter, all the dark regions we are going to make darker. But what happens that this kind of an operation we are going to do uniformly over the entire image. Now it may be so that some of the pictures, okay, some of the pixels in that same picture, okay, are having some intensity values, okay, which are really speaking not very dark, okay, but because of the poor contrast, okay, it has appeared, the intensity appeared to be almost same as that of the pixels which are supposed to be bright, okay, pixels which are supposed to be bright but hasn't appeared very brightly, okay. Its intensity should have been, pixel intensity somewhere should have been say 200 or 240, but the pixel intensity which we find in the picture may be 120. Now there are some pixels whose genuine intensity value is also 120. Now in the case of contrast enhancement, what you are going to do, that 120 you are going to stretch up to 240 or all the way up to 255 if your dynamic range permits that. But while you are stretching that, you are stretching not only the pixels which are supposed to be bright, okay, and which should be stretched, but you are also stretching some of the signals, okay, which are not so bright, okay, which are not supposed to be bright, but as a result of applying that kind of a transformation, you are stretching those pixels also, okay. So you are not improving the image in every respect, okay, you are only improving those regions of the image, okay, where the contrast is poor. If an image contains, okay, some areas where the contrast is already good, or where the contrast really, really speaking, there is not supposed to be remarkable difference in the intensities, even in those regions also you are going to artificially create some difference in intensities, okay, which are really not supposed to be there in the picture. So it may be so that while doing the image enhancement, okay, you are doing improvement in some areas of the image, and you may make, okay, deterioration also in some areas of the image. And everything after all depends on the objective. Again, let us take the case of edge sharpening. We are interested in taking out the edges. Now what we will do by the image processing operation is that we will extract the edges and we will make the edge boundaries, okay, boundaries of the object, okay, more prominent, or the features which are present, okay, we are going to make those features more prominent. But that doesn't mean that we are improving the contrast, okay, or we are eliminating the noise. The techniques might be different. So it is only improvement of the edge boundary that we are trying to do. So it is most important to specify, whenever we are specifying the image enhancement, okay, it is very important to specify that you are wanting image enhancement of what feature. That must be very clearly spelled out. Alright. So since I have listed all these various image enhancement requirements, okay, we are going to study one by one all these techniques. Alright. Now the overall image enhancement techniques, one can divide into two distinct methods, okay. The subject of image enhancement can be distinctly divided into two broad categories, okay. The one technique which we apply is called as the spatial domain enhancement technique. In spatial domain enhancement technique, what we are doing, we will simply modify, okay, the grayscale values or the intensity values of the pixels directly, okay. That means to say we will operate at the UMN domain, where U is the image intensity function, okay, Mn are its indices, okay. So we are going to modify the values of the grayscale or values of the intensity, okay, which are present in the image. So in the spatial domain technique, we will directly operate on the intensity values, whereas the other technique is known as the transform domain technique. In the transform domain technique, what we do, we transform the original image into a transformed array by applying some unitary transformation, like the discrete Fourier transform, the Walsh-Hadamard transform, or the discrete cosine transform, KL transforms, all the transform techniques which we have studied so far. One can apply those transform domain, one can apply those transformation techniques, and on the transform domain values, okay, that is on the VKLs. Now if you modify the values of VKLs which we get in the transformed image, okay, then, and after modifying the transform coefficients VKL, you apply an inverse transformation to get back the image, okay, or an enhanced image, okay, which you get in the process, okay. Those kind of image enhancement techniques we will classify under the transform domain image enhancement techniques. Now at first I will begin with the spatial domain technique. So today we will start with the spatial domain techniques of image enhancement. Now in the spatial domain approach, okay, it is the image processing function can be expressed something like this. Supposing f of xy, okay, happens to be our input image. So our input image is given by the function f of xy, okay, where f, the function f happens to be the intensity value at the pixel located by x and y, okay. Now given this input image, okay, we would like to get an output image, okay, or rather a processed image. Let me now start calling it as a processed image. So our objective is to get a processed image, okay, which I will not write as f of xy because the same image function will not be there. The processed image I will write as g of xy, okay, where g of xy happens to be the intensity value at the location xy after processing. I repeat, g of xy is the image intensity value at the location xy after doing the processing. So our image processing function can now be written as follows. So g of xy is somehow related with definitely the f of xy, because obviously whenever we are wanting the processed image must be somehow obtained by doing some operations on the input image itself, okay. So this g of xy should be some function of the input image, and let me call that function as a function t. So the overall expression which I get is that the processed image's grayscale value g of xy is going to be some function of the intensity value of the original image. Now what kind of a function is this? That is the most pertinent question. What is this t? Or rather, in which domain the t is defined? Now typically it is so found that the image intensity of the processed image, the intensity of the processed image at a particular point xy, okay, does not depend upon the input intensity at the point xy alone, okay. It is also dependent upon the intensities which are there in the neighborhood of that point xy, okay. So we consider a neighboring region around that point xy and consider all the intensity values within that neighborhood region, okay, and then we apply some function, okay, if that function t which we are going to design, okay, if that function t is defined over a neighborhood region of xy, okay, then what we get by applying that function is the image intensity value at that point xy, okay, intensity value of the processed image at the point xy, and that is what we get. So naturally this t in general I must consider it to be a neighborhood operation. So pictorially it will look something like this. Supposing this happens to be my x-axis, or rather say this happens to be my y-axis and this happens to be my x-axis, okay, and supposing this is the area over which the image is defined. So that means to say 0 to n minus 1 and again 0 to n minus 1 over here. So it is an n by n image that I am considering. Now take a particular point xy. Supposing this is the point xy that I have considered. Now around that point xy, okay, let me define a small sub-image. Or the idea of this sub-image is that I would like to choose a neighboring region around this point xy. So let me choose a neighboring region like this. So that means to say with the point xy as the center, okay, I have chosen a sub-image. Now here, just for the case of simplicity, I have chosen a rectangular, a square sub-image. I have considered a square sub-image, okay, but there is no hard and fast rule, let me tell you, that you have to choose a square sub-image only. You can choose a rectangular sub-image, okay, or you can choose other shapes of sub-images, like you can choose a sub-image of circular shape, you can choose a sub-image of elliptical shape, a sub-image of diamond shape, a sub-image of hexagonal shape, and so on. Many types of shapes are possible which you can choose for the sub-image, but generally for the simplicity of operations in the image processing, square sub-images or rectangular sub-images are more common, okay. So let us consider a square image, a square sub-image, and again you can ask me that what is going to be the size of that square sub-image, okay. To this my answer will be that right now I am not putting any restriction on the size of that sub-image, okay. That sub-image could be very small and that sub-image could be quite large. It again depends upon what kind of an application we are looking for. So let us keep it free, okay. We will answer this question, that what should be the size of the sub-image, okay. This question we will answer little later on. We are keeping an open mind on this, okay, saying that at first let us not put any restriction on the size of those sub-images. Now what you have to do is, for this particular pixel xy, whose coordinates are xy, you are going to determine the function g of xy, the intensity value of the processed image. And the intensity value of the processed image is very much dependent upon, if we go over to the f domain, f means the original input image. The original input image, if I go, then I have to take the intensity values at the point x y minus 1, or rather this is going to be x minus 1 y minus 1, x minus 1 y, x minus 1 y plus 1, and so on, all these 9 pixels which are there, because I have considered a 3 by 3 sub-image size. I need not have chosen 3 by 3, I could have chosen 5 by 5, I could have chosen larger size sub-images. As I told you that I am not putting any real restriction on this. So what happens is that the g of xy is dependent upon the neighboring intensity values within this sub-image. And the function t, okay, you can ask me that what kind of a function is that function t. Again I am not putting any restriction. I can only give you some example. Supposing I tell you that the function t is defined in such a manner that t of fxy means that it is f of x minus 1 y minus 1 plus f of x minus 1 y plus f of x minus 1 y plus 1 plus f of x y minus 1 plus f x y plus f x y plus 1, okay, plus so on so on. All that I am trying to do is that I am taking this 3 by 3 neighborhood and I am just summing up the intensity values of all these pixels, and then since there are 9 pixels I am just dividing it by 9. So what am I doing in the process? I am doing a kind of averaging. Let me very clearly tell you, I mean, you had said that it is averaging. Actually it should be very clearly specified as a local averaging, because averaging means you are not doing the averaging of the entire image. You are doing the averaging only on a sub-image, and that sub-image is a local sub-image. It is defined centered around xy. So what you are doing basically is that in order to determine the intensity value for the processed image g of xy, you have applied this sub-image with xy at the center, I mean at the position xy, with xy as the center, you have applied this sub-image, and after doing this transfer, after doing the operation that is specified in the function t, okay, you are going to determine g of xy. So at the end what you are doing, you are determining the, when the sub-image is located exactly centered around xy, what you are determining? You are only determining the intensity value of just one pixel. You are only determining g of xy. If I ask you that what is going to be g of x plus 1 y, what should you do? I should shift this sub-image by 1 pixel. Okay, if I want to do g of x plus 1 y, then instead of picking up the sub-image over here, okay, I should relocate my sub-image somewhere over here, so that its center now becomes, this is the point, if this is the x-axis, this is the point x plus 1 y. So I will shift this sub-image. Okay, if I want it at some other point, let us say if I want the intensity value at the position g x y minus 1, okay, what I should do? I should shift this window, okay, if this is my original position, then x y minus 1 means I should shift the window or shift the sub-image over here. So now if I ask you that I am interested in computing the gxy values, okay, for I am interested in computing g of xy for all values of x 0, 1, etc., up to capital N minus 1, and y equal to 0, 1, etc., up to capital N minus 1. If I want to compute the gxy values for every pixel, okay, what should I do? I must move this sub-image, okay, over the entire image space. Okay, I will start like this. If this is my y-axis and this is my x-axis, okay, and if this is the image space n minus 1, n minus 1 starting from 0, at first I will apply the sub-image over here, okay, then from the top left I will start, I will keep on, then I will compute the intensity value at g of 0, 0, and then I will keep on shifting this sub-image, okay, till the time I reach the bottom right, okay, the bottom right pixel, till the time I reach that, that is to say g of n minus 1, n minus 1, till I reach that point, I will keep on sliding this sub-image. Alright, so this is a kind of spatial operation, okay, which we are going to do, okay, because the basic function which we define, okay, let me go back here, the basic function which I had defined, g of xy equal to t, some function t over f of xy, I have defined this t over a specific subimage or over a neighborhood centered around xy, okay. Now again I told you in the beginning that don't bother about the subimage size because I am going to keep it free. So let me begin with a very small subimage size, very small subimage size. So to start with, let me take a very small subimage size. What is the smallest subimage size that I can take? Yes, 1 by 1. 1 by 1 could be the subimage size, and what does it mean? That means to say it is the pixel xy itself. So what happens is that if I go over to a pixel xy, okay, then g of xy is a function of f of xy only. It is not a function of f of x minus 1 y, f of x plus 1 y, all these things. It is a function of f of xy only. So when the subimage size is 1 by 1, the simplest subimage that I am taking, then g of xy is going to be, okay, a function of f of xy, okay, where the function t is defined only for the point xy. The function t is not defined for points other than xy. So what really it means? It means that if I have the intensity value, if I have an intensity value at a point pixel, at a point xy, okay, in the input image, okay, then the intensity value at the same point in the processed image is going to be dependent upon the intensity value of this pixel only. So is it a local operation? It is obviously a local operation, but it is a very, very restricted local operation. It is a point operation. We are going to take this kind of operations where the subimage size is 1 by 1. We are going to call them as point operations. We are going to tell them as point operations, or the literature very often describe them as a zero memory operation. Many a times the literatures describe it as zero memory operation. Can you tell me why they have given the name zero memory over here? Because in order to determine the image intensity value at a particular pixel, okay, you need not store the entire image, you need not even store the neighboring region around xy. All that you have to do is pick up the intensity value at the point xy, okay, and depending upon what kind of a transformation it is, you determine the intensity value of the processed image, okay. So you really don't have to store the entire image, you don't even have to store the neighborhood region of the image. So it is called as the zero memory operation. So now analytically I am going to write it in a bit of better way. So that means to say that given a gray level, okay, a given gray level, u, okay, well let us assume that u is in the range of 0 to capital L, okay, this u is mapped into a gray level V, okay, which belongs to the domain again 0 to L, okay, according to a transformation, according to the transformation, a very simple transformation. V is going to be a function of U, isn't it? So you have the original intensity as U, which is defined over the range 0 to L, okay, is to be mapped into yet another gray level V, okay, which is defined over the range 0 to L according to a transformation like this. So that means to say that if I draw a graph like this, okay, and on the x-axis if I plot the values of U, U is going to be in the range of 0 to L, alright. So U is in the range of 0 to L, and even V is also going to be in the range of 0 to L. This is the output V. Now this is the input and this is the output. So the curve that I get defining the input output relationship is a transfer function. Basically it is a transfer function that we have to consider. Now I can take various types of transfer functions, okay. Supposing I take the transfer functions like this. So this is 0 to L, again this is 0 to L, and supposing that I happen to take a transfer function of this nature, okay, that means to say where the slope of this line, okay, the slope of this line I take as unity plus 1. If I take a transfer function like this, what do I get really? The intensities don't change from input to output, the intensities don't change. So whatever is the input image, the processed image, or rather the output image, is going to be same as that of input image. So by taking a transfer function like this, okay, I can mathematically define the transfer function as V equal to U for U lying in the range of 0 to capital L. But what is the use? We will not be having a transfer function as simple as this, because otherwise there is no point in doing an image processing if your input image and output image are the same, okay. So we have to do some operation where the input image and output image are going to be at least different. So let me take a generalized transfer function of this nature. Supposing I take, again I take this to be my V axis and this to be my U axis, okay, and I define a transfer function of this nature. Supposing this is my L, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, okay. So this is L. So 0 to L in U and 0 to L, or rather it should have been L minus 1 anyway. So 0 to L in the case of V. And supposing my transfer function is like this. What do you see in this type of transformation function? Supposing I call this intensity as A, this intensity as B, okay, and the corresponding output intensities I call this as, let's say, VA, and I call this intensity as VB, okay. So in this type of a transformation function, what I am doing is, basically this transfer function can be divided into 3 distinct regions. First is this straight line, the second part is this straight line, the third part is this straight line. And just observe one thing, that the slopes of these three straight lines are clearly different from each other. For the first straight line, let me call the slope as alpha. The slope of the first straight line is alpha. The slope of the second portion of the straight line, that is the one. So the straight line which is defined for 0 to a, the slope is alpha. The straight line which is defined for a to b, that is beta. And the straight line which is defined for the rest of the portion, that is b to l, I consider its slope as gamma. Now you find that some slopes are lesser than unity, some slopes are greater than unity. In this kind of a diagram which I have shown, I have intentionally chosen beta to be greater than unity and alpha and gamma happen to be lesser than unity. So if I apply this type of a transformation, okay, can you tell me what do you expect at the output image or the processed image? What we will do is that in between the range A and B, okay, we are improving. I mean, between A to B, the actual original intensity is changing only this much. Original intensity is changing by a small amount, okay, that is B minus A. Whereas in the output, it is changing between VB minus VA, okay, which is a quite large range. So that means to say, in this particular zone, okay, in the second zone, we are stretching the intensity. And in the other zone, 0 to A, we are compressing the intensity. Again, between B to L, since the slope is less than unity, I am compressing the intensity. So basically, in this type of a transfer function, what I try to do is that I want to enhance the contrast only within the range A to B. Okay. Now, mathematically, the transfer function can be defined like this. Now, the transfer function for this can be written as, if V is the output intensity, I can write it as, yes, you can help me in formulating the transfer function mathematically. When I have U within the range 0 to A, what should be the relationship between V and U? Alpha U, correct. When U is in the range of A to B, that is A less than or equal to U less than B, when I have that, alright, what are you going to have? It is going to be beta times U minus A plus VA. Let me write down separately because otherwise you may feel difficulty in reading it. Let me write it afresh. So V is equal to alpha U when U is in the range of 0 to A. V is equal to beta times U minus A plus VA, okay, when I have U in the range of A to B, and I have V equal to gamma times U minus B plus VB when my U is in the range of B to L. Okay, just verify it from this transfer function only. In the range U lying between A to B, okay, the function is beta, okay, the slope times U minus A plus VA. It is satisfied. Just substitute here U equal to A, you substitute, okay, that means to say this point, and you get V equal to VA. So you are getting this point, and whenever you are considering the other extreme, that is whenever you are considering U equal to B, okay, in that case you will get this as VB. Okay, so basically I mean, of course, U equal to B, if you take in this relation, you are getting V equal to VB, and in between it follows this slope of beta. Okay, so this is a general transfer function which I have considered, okay, assuming that the transfer function can be divided into 3 distinct regions. Okay, and now what I will do is I will simply manipulate between this alpha, beta and gamma values, okay, and show you various type of image enhancement functions that I can get in the process. Okay, I can take various values of alpha, beta and gamma. I think I have already considered a very trivial case of alpha equal to beta equal to gamma equal to 1, in which case it is V equal to U. It's a very trivial case because it becomes the original image itself. Now I consider some of the non-trivial cases, okay, and let us take a case 2 in which I have alpha equal to gamma equal to 0. Okay, look at this transfer function back. I have taken alpha equal to 0, gamma equal to 0. Okay, beta exists as a non-zero slope, okay, but alpha and gamma have been made 0. So what is the transfer function that results? Okay, I mean pictorially the transfer function will look something like this. If this is the U axis and this is the V axis, if this is A and this is B and this is L, okay, then what we are getting is that between A to B I have a slope beta, and then I should draw it with a different color so that it appears more prominent. Just see, the transfer function is of this nature. That means to say, in between A to B I have a slope beta, but between 0 to A the slope alpha is equal to 0. Between B to L the slope gamma is going to be equal to 0. Okay, so what we are doing, we are only enhancing or expanding the contrast in the zone A to B, and all the intensities which are there in the zone of 0 to A and in the zone of B to L, okay. Now we are going to make the intensities in the domain 0 to A as 0, and the intensities which are there in the domain B to L, I am just saturating the intensity for all of them to the maximum value, that is equal to L. So in this case what I get is that as long as U is less than A, I have V equal to 0, and when I have U greater than or equal to B, okay, I have V equal to the maximum value. Now this kind of a transfer function which follows this case 2 is called as a clipping function. This is called as a clipping function because very clearly see that any intensities, okay, which is not following within the zone of A to B, okay, is getting clipped. If you are knowing that how the clipping takes place in the case of amplifiers, okay, when we have a transfer function, okay, where the where there is a saturation, where there are saturating limits, then you get a clipped waveform as the output of your system, okay. Very similarly, even here also there is a clipping. Other than this A to B zone, okay, rest are getting clipped. Alright, so it is a clipping function that results. Now I consider the case 2 only, that is to say I still continue to take alpha equal to beta equal to 0, but what I am doing, I am progressively reducing the difference between A and B. I am going to bring A and B nearer to each other. If I do that, what results gradually? The slope. Firstly, that if I reduce the width between A and B, my slope beta will keep on increasing as I bring A and B closer. In the limit, when I make A equal to B, okay, that means to say I consider the limiting case where A is equal to B and that I define to be some value T, then what happens? then the nature of the transfer function will be like this. I have 0 to L in U, and I have 0 to L in V, okay, and this is supposing the point T. So what happens that all the intensity values, okay, which are there in the range of 0 to T are made 0, and all the intensity values which are in the range of T to L are made equal to L, okay. So what is the nature of the output image that you get, the processed image? Processed image is a binary image because it can assume only the intensity values equal to 0 or L, nothing in between, okay. So it results in a binary image, okay, and this type of a function is called as a thresholding function. Thresholding function, okay. So this is a special case of 2. All right. Now I consider some other interesting transformation function. I take this to be the V axis, this to be the U axis. So this is 0 to L, and this is 0 to L, and supposing my transfer function is like this. So I can write mathematically the transfer function as f of u, okay, or rather v is equal to f of u, and this is written as capital L minus u. So when u is equal to 0, when the input intensity is 0, the output intensity is maximum, and vice versa. When the input intensity is maximum, the output intensity is 0, and in between 0 to L it is gradually falling, means as the input intensity increases, the output intensity decreases. Now what is the kind of image that you are going to get? It is a simple negative image, okay. This transfer function results in a negative image, or it's a gray level reduction, gray level reversal, I can say, sorry, gray level reversal, okay. Now let me take another interesting transfer function. I take the V axis over here, and I take the U axis over here. Again I assume this to be L, 0 to L, and supposing I take this to be L, okay. Now what I am doing is I am making the image intensity, I mean the transfer function of this nature. That means to say, between the limits a and b, okay, I make v equal to L when u lies between a and b, okay, and it is 0 otherwise. So it results in a transfer function like this. So what is the nature of the image that you get in the process? So what we are doing is only the intensities which are falling, when only the input intensities which are falling in the zone of A to B, okay, are being highlighted, okay, and rest of the pixels are forcibly made black pixels, okay, so that I can only highlight the intensities in the region A to B, and this is known as a as an intensity level slicing. This is called as intensity level slicing. I am only cutting out a slice, the zone A to B which I take, okay, I am only cutting out that particular slice, okay, and I am representing this. All right. So this is the intensity level slicing that I do. All right. Now all the background information is lost. Now can you tell me, if I want to highlight the intensity zone A to B, but at the same time I would like to preserve rest of the background, then what type of a transfer function should I use? Unity slope elsewhere. So instead of making V equal to 0 elsewhere, I should make V is equal to U elsewhere. So the nature of the transfer function, okay, will be something like this. So the transfer function which I have just now drawn with green, okay, can be written mathematically as V equal to L within limits A less than U less than or equal to B, and V is equal to U otherwise. Okay. So this I am going to call as intensity level slicing with background. I am going to call this as intensity level slicing with background, and the earlier operation I am going to call as intensity level slicing without background. This is without background. So that means to say that the curve which I have traced with pink, the curve which I traced with pink is the intensity level slicing without background, and the curve which I have traced in green pen, okay, is the intensity level slicing with background. All right. So these are the various, these are some of the various transforms, or rather point operations, okay, which can be carried out, or these are some of the typical image enhancement functions, okay, which are available. But we will study more of it in the next class. All right. Thank you.